Hello everyone, this is Dennis of KO Math. Welcome back to my channel. Today I'm going to share with you some strategies that you can use to evaluate these limits at infinity and other related problems. Let's get started. Consider this first limit problem. Can you determine immediately what the limit is? It is equal to negative 5 halves. To make this limit obvious in the class, we usually do the following. So we look at the highest power of x in the denominator. So here we have x cubed. And then we divide all the terms in the numerator and in the denominator by this x cubed. So we'll get here limit of this expression. And then we simplify each fraction. Okay, and we'll get here 5 minus 2 over x plus 1 over x cubed all over 3 over x cubed plus 4 over x squared minus 2. So here it is clear that when x becomes large, okay, becomes a huge number, so this fraction here will approach 0, and also this one will also go to 0 because the denominator is a large positive number. So it will go to 0. This term will also go to 0. So we usually use the theorem that states that the limit of a non-zero constant over x to the n, when n is a positive integer, as x goes to infinity or as x goes to negative infinity, is equal to 0. So from this, it is clear that the limit, so the numerator goes to 5 and the denominator goes to negative 2. So the limit of this rational function is equal to negative 5 halves. Now, how do we determine the limit of this rational function quickly? Just keep in mind that the highest degree term of a polynomial dominates the other terms as x goes to infinity or negative infinity. So here, the value of 5x cubed dominates the value of negative 2x squared plus 1 as x goes to infinity. And actually, it's true also when x goes to negative infinity. And also in our denominator, the value of negative 2x cubed dominates the values of a 3 plus 4x. In other words, here as x goes to positive infinity, this 5x cubed outgrows these terms, negative 2x squared plus 1. And in terms of graphs, we say that the graph of this polynomial function y equals 5x cubed minus 2x squared plus 1 looks like the graph of y equal to 5x cubed when x goes to infinity or when x goes to negative infinity. Therefore, the limit of this rational function is just the limit of the quotient of the highest degree terms. So we have here 5x cubed over negative 2x cubed. And then we just cancel the common factors. So that gives us limit of a constant as x goes to infinity, but the limit of a constant is equal to the constant. So therefore, it's equal to negative 5 halves. In general, if we're looking for limit as x goes to infinity or x goes to negative infinity of a rational function, so let's say we have limit of a polynomial of degree n over a limit of a polynomial of degree m. So here a sub n is not equal to 0 and b sub m is not equal to 0. The limit is just equal to the limit of the quotient of the highest degree terms. So it is equal to the limit of a sub n x to the n over b sub m x to the m. And in this case, if the degree of the numerator, the n, is less than the degree of the denominator, which is equal to m, then the limit is just equal to 0 because when we cancel the common factors, we'll be left with some factors of x in the denominator. So when we take the limit, so the denominator will go to positive infinity or negative infinity. So therefore, the limit of a non-zero constant over a large positive number or a large negative number, so that is equal to 0. Now, what if the degree of the numerator n is larger than the degree of the denominator m? So in this case, when we cancel the common factors x, then we'll be left with some factors of x in the numerator. So therefore, the value of the numerator will either increase without bound, so that is, will go to infinity, or will decrease without bound. So and the limit of the denominator is just constant. So the limit of this quotient will be either positive infinity or negative infinity. And in the case where n is equal to m, just like what we have here, so degree of the numerator is 3, degree of the denominator is equal to 3. The limit is just, of course, we have same number of copies of x in the numerator and number of copies of x in the denominator. So we cancel those factors. We're left with a sub n over b sub m. So if the degree of the numerator is the same as the degree of the denominator, the limit of the rational function is just the ratio of the coefficients of the highest degree terms. So in this case, we have 5 divided by negative 2, which is equal to negative 5 halves. We now use this technique to evaluate the remaining limit problems quickly. So let's move to the second problem. So here we want to find the limit of this rational function. This is just a polynomial over a polynomial. And from the technique that we have, the limit of this is just the limit as x goes to negative infinity of the highest degree term in the numerator over the highest degree term in the denominator. And what do you think is the highest degree term in the numerator? So this term here, when you expand this, you'll get the highest degree term, which is equal to x cubed. And here, when you expand this one, you'll get the highest degree term, which is equal to the cube of 2x, which is equal to 8x cubed. So the highest degree term in this numerator is 8x cubed plus x cubed. So that is equal to 9x cubed all over. So the highest degree term in the denominator is 9x cubed, and then we cancel the common factors. So cancel, 1, 1. So the limit is just what? This is limit of 9 over 9, which is actually equal to 1. So we can also cancel the 9, 9 here, replace it by 1. So this is just limit of a constant. Limit of 1 as x goes to negative infinity. Of course, it's equal to positive 1. Next problem. So let's find the limit of this expression. So here we have absolute value of x cubed minus 4x squared. So here we're looking for the limit of this expression as x becomes large negative, as large as we want, as large negative as we want. So take note that when x goes to negative infinity, x is a large negative number. So therefore, this x cubed minus 4x squared is dominated by the value of x cubed. So, and the value of x cubed, when you cube a negative number, it is a negative number. So we expect that as when x becomes a huge negative number, then this number inside of this absolute value is a negative number. So therefore, how do we remove absolute value bars when you have a negative number inside the absolute value bars? You just have to take the negative of the number inside. So here we can write this down as limit as x goes to negative infinity of 5 minus the negative of the number inside. So it is like negative of x cubed minus 4x squared, okay, which is actually equal to so this numerator here, so minus negative, it becomes 5 plus x cubed and then minus 4x squared. So this is the same thing as this expression here is the same thing as 5 plus x cubed minus 4x squared all over the denominator, which is equal to 2x cubed plus x squared minus 8. And then again, we use our technique. The limit is just the limit of the ratio or the quotient of the highest degree terms. And what are the highest degree terms here? X cubed over 2x cubed. And they are actually of the same degree, so the limit is just equal to, we can cancel this common factor, replace them by 1. So limit of 1 half as x goes to negative infinity is just 1 half. But you can determine quickly the limit of this expression just by looking at it. So the numerator is dominated by x cubed, and x cubed is a negative number as x goes to negative infinity. So absolute value of x cubed is just the negative of x cubed. So minus negative x cubed is just positive x cubed, and then same degree, numerator and denominator have the same degree. So therefore, the limit is just the ratio of the coefficients, which is 1 over 2. For this next problem, so even if the numerator contains radicals, we can still apply the same technique that we applied to solve the previous limits. We just have to remember that a polynomial is dominated by the highest degree term when x goes to infinity or when x goes to negative infinity. So the limit of this expression is the same as the limit of square root of the highest degree term, which is 4x squared, minus the highest degree term of x squared minus 5, which is x squared, all over highest degree term in the denominator, which is negative 3x. Now, this is the same thing, limit as x goes to infinity. So x goes to infinity, so x is a positive number, so square root of 4x squared is just 2x, minus the square root of x squared is x, all over negative 3x. So here, the limit I think is already clear. So this is equal to x over negative 3x, and we just cancel the common factor x, okay, between the numerator and denominator. So we'll get here, cancel 1, replace it by 1. So the limit is just what? Limit of a constant, limit of 1 over negative 3. So that is equal to negative 1/3. Suppose we want to find the limit of the same expression, but this time as x goes to negative infinity instead of positive infinity. So here, we replace this one, x goes to negative infinity. Again, to find the limit, so we just have to find limit as x goes to negative infinity, square root of the highest degree term, square root of 4x squared minus square root of highest degree term, x squared, over the highest degree term, which is equal to negative 3x. But be careful with this one. This is the common mistakes of students, is to, for example, write square root of x squared as x and square root of 4x squared as 2x. Here, x goes to negative infinity, so x is a negative number. So take note, square root of x squared is actually absolute value of x. So when x is negative, absolute value of x is the negative of x. So here, when you take the square root, when x is negative, then square root of 4x squared will be negative of 2x. And does it make sense? Yes, because when x is negative, negative 2 times a negative number is a positive number. And square root of a positive number is a positive number. If you write this down only as 2x, then you're saying that the square root of a positive number is 2 times a negative number, which is negative. So it's incorrect if you don't have a negative sign here. So similar explanation for square root of x squared. So this is minus negative of x, and then all over negative 3x. So this is equal to limit as x goes to negative infinity. So this is negative 2x plus x, so that is negative x over negative 3x. Just cancel the common factor x, and the limit is just 1/3. We can also evaluate these limits using the other technique that we used a while ago. That's dividing the numerator and denominator by x, and then simplifying the numerator and denominator, and then we take the limit as x goes to infinity. But be careful when you're doing this limit as x goes to negative infinity, because you cannot replace here x as square root of x squared. Take note that x is negative, so you need to write the x as the negative of square root of x squared, or that is square root of x squared must be equal to negative x. Now consider the following limit. What do you think is the limit of this function as x goes to infinity? So if I look at it, I can easily determine its limit, and the limit is equal to negative infinity. So again, we apply similar reasoning here as what we did in the previous problems, because in this case, as x goes to infinity, e to the x goes to infinity, and actually the numerator and denominator are polynomials in e to the x. And if we want this function to look like a rational function, then we can make a substitution. For example, we can let this e to the x equal to t, and we'll get this expression. So e raised to 3x will be equal to t cubed, and then e raised to 2x will be t squared. And take note that as x goes to infinity, this t, which is equal to e to the x, also goes to infinity. So we can have here limit as t goes to infinity of this rational function. And then, as we said, so these polynomials are dominated by their highest degree terms. So the limit is just equal to the limit of the quotient of the highest degree terms, which is equal to, if we simplify this, it's equal to t over negative 6. So as t goes to infinity, t over negative 6 goes to negative infinity. And we can actually also show this limit using the other technique that we used in the previous problems. So in this case, we divide the numerator and denominator by the highest power of e in the denominator, so that is e raised to 2x, and we'll get this expression. And we simplify these fractions first before we compute for the limit. So we can write this down as e to the x. This expression is 3 over e to the x, and then this one, the same thing. And then this can be simplified as 1 over e to the x. And as x goes to infinity, e to the x goes to infinity, while this for fractions goes to 0. So therefore, the limit will be like infinity over negative 6, which is equal to negative infinity. Let us now consider this limit problem. At first, it looks like this is of a different type because x here goes to a finite number. And in the previous problems, x goes to either from goes to infinity or negative infinity. But actually, this and the previous problems are of the same type because as x goes to 0 from the right, ln x goes to negative infinity. And we can think of the numerator and denominator as polynomials in ln x. And since the degree of ln x in the denominator is higher than the degree of ln x in the numerator, we expect that the limit will be equal to 0. We can also make a substitution here for this function to look like a rational function. If we let ln x be equal to t, then we can write this down as 4 plus 3t raised to 5 over 2t raised to 6 minus 50. Clearly, the limit is equal to 0. Now let's move to our last problem. So we want to find the limit of this expression as x approaches pi over 2 from the left. So similar as in the preceding problem, so as you can see, if we approach pi over 2 from the left, tangent x approaches infinity. So in this case, we just consider this as a polynomial in tangent x. So they are actually of the same degree as a polynomial in tangent x. So the limit is just equal to the coefficients of the highest degree terms. So therefore, we can already determine the limit, which is equal to negative 1/4. Now, if we want to make substitution again, just like in the previous problem, so we can have t equal to tangent x, and we can write this down as t squared minus 5t over 10 minus 4t squared. And clearly, the limit of this as t goes to infinity, so take note, as x goes to pi over 2 from the left, t, which is equal to tangent x, goes to infinity. So the limit of this, same degree, take the ratio of the coefficients of the t squared, and we'll get negative 1 over 4. Before we end this video, let's review the technique that we use to evaluate limits. So if you know that if you have a function that goes to either infinity or negative infinity, as x approaches, for example, infinity, negative infinity, or a from the left, a from the right, or a, then the limit of this, it's like a rational function in f. So you have a polynomial in f over another polynomial in f is just equal to the limit of the ratio of the leading coefficients or the highest degree terms in terms of f. Okay, so in this case, the limit is just equal to 0 if the degree of the numerator is less than the degree of the denominator in terms of f. And if the degree of the numerator is larger than the degree of the denominator, then the limit is either infinity or negative infinity. And the limit is equal to the ratio of the coefficients of the highest degree terms if they have the same degree. Okay, that's everything I have for you today. If you enjoyed the tips that you learned in this video, please hit the like button below and share this to your friends. Also, don't forget to subscribe to my channel to see the new videos that I release every week. Again, this is Dennis of KO Math. Thank you and see you next time.